Once again, welcome back to Mirabilis Design's webinar series on enabling better products using system-level design. Today, I'm your host, Deepak Shankar, and I will be talking about multi-die, more specifically, optimizing chiplet architectures with RISC-V clusters, GPUs in AI engines to solve your performance and power limitations and requirements. When we look at chiplets, the reason or the purpose for chiplets is really as an alternate to monolithic dies. As the functionality keeps increasing, the die sizes keep increasing. But unfortunately, the market is also requiring new products at a much faster rate. So to quickly respond to market requirements, the concept of multi-die or 3D ICs have come into play. In addition, there are a number of IP vendors that are transitioning over to providing modules that can quickly be reused to create new products. Of course, there is always this concept of multi-die going the direction of reducing cost because each element within the die can be built on a different process. The different quantities can be constructed, and also there can be localized cooling. One of the biggest advantages that a smaller dedicated die for different parts of your system is really the increase in reliability because of smaller size and greater process efficiencies. One of the things that generally does not happen with chiplets, and something that a lot of people should be aware of, is that you don't necessarily get improved performance or lower power just because you transition to a 3D IC. One of the original concepts and the motivation for multi-die was to collapse a complete board to a single package. That also explains why the standard for the interconnect across multi-die is UCIe, which is very close to PCIe 6.0. In this case, if you look at it, I have a complete communication system, which I can transition out into a single package. And each of these components that you see that are discrete components that you can buy off the shelf are now integrated into the single package. Obviously, when you start integrating so much of functionality that goes on a single board into a single die, you have a lot of challenges. There are power challenges, performance challenges, packaging challenges, cooling challenges, a variety of things. So, for example, when we look at the performance challenges, you will see, for example, what's the latency between the chiplets? Is there any sort of buffering? Are there any CPU latency that is outside of a large range? And of course, the biggest thing is what is the throughput I'm getting on any of my compute components? Is the throughput matching up with my requirements, or is the throughput lagging? When you have interconnects, you obviously have a lot of standards, and these standards lead to a lot of parameters that can be tuned to create your customized version. Similar with UCIe, which is you have package type, which can be standard or advanced. You have maximum link speed of gigabit transfers 32 gig, but there are slower transfers as well. You can have a maximum modules of 4. You can have transmitter and receiver buffers. You can have the kind of protocol you would need on the interconnect inputs. And of course, the most important thing is flit size and the flow control between the flits. When you want to really integrate these subsystems, one of the areas where there's huge opportunity is in very large systems. So you can look at things like avionics, intelligent equipment, industrial systems, medical electronics, data centers. All of these offer a huge opportunity to be able to reduce your area cost and performance and power consumption. So if you take a large system like an avionics here, there are so many networks, so many analog systems, so many interconnects, power systems, sensors, processing units, and so on. You have now the opportunity to take all of these individual components and collapse them down into different dies. So essentially, a board that might be about, say, 2 feet by 2 feet can now be collapsed into a small single chip. And this obviously reduces your cost, your structural area, your cooling effects, which means essentially a avionic system designer or a satellite or a payload system designer could essentially add more instruments, add more functionality, add more payloads into your application. So really what multi-die is doing is enabling you to add more functionality and have a quick turnaround. UCIe is something that everybody's hearing about. It is a standard. It's now at a higher stage and it's evolved quite considerably. But in the past, there have been a lot of companies that have used multi-die and they built their own standards. So we've got anywhere from NVIDIA to Intel that had their own proprietary standards. Unfortunately, tier two semiconductor companies, startup companies, things like that, do not have the ability to do research and create their own interconnect. Also, they'd want to reuse IP from different vendors. How do you do it? The best one is to have a standard for the interconnect between the dies. Also, when you have a standard, it becomes more predictable in terms of performance and power. The areas where these are very applicable are gaming, data centers, 5G, AI, and also I was showing you a lot of space-based applications as well. Now, one of the things that also happens, and this is a very critical aspect, is that you can potentially create standardized modular die sizes. Why is this important? Is because this becomes very important when you want to like add on new dies to create a new functionality without replacing, say, your core processing unit or your core compute unit. So it kind of becomes the same thing that you would have in a data center where you have racks and server chassis that have fixed sizes. You can now do the same thing with chips as well. What is system architecture exploration? The system architecture exploration is the ability for you to be able to evaluate very quickly what is your options, what is the best way for you to implement your product. So when you look at it, each of these dies could have separate interconnects, could have separate compute resource, separate scheduling, separate memories, things like that. And what you need to do is you need to consider how you're going to put them all together. And the way you're going to put them all together is by figuring out, one, what is your application? And two, what are the requirements in terms of both performance, power, area, costs, resources, efficiency, failures, assurances, and things like that. Now, there's always a lot of different options available, and you really want to understand which architecture is best suited for your application. Now, once you created this application, say you have different dies and each one has their own different processing, the next question comes up is, how do you take tasks and apply them to these different subsystems? So what's the flow that happens here? Now, what happens when you add a second die? What is the interference between these different applications? How could you schedule it so that you don't overwhelm the system by consuming almost peak power? And also be able to detect anomalies. For example, here, I have a situation where I tried two different experiments of buses, 200 and 400 megahertz. If you look at this design, you will see that the 400 megahertz actually has peak values that are much higher than the 200 megahertz. Yes, of course, the 400 megahertz is in a lower power range versus the 200 megahertz, but you can see these peaks are there. So in this particular design, going from 200 to 400 megahertz is not really an advantage. And this is where system modeling really comes into play. System modeling is the process of being able to do architecture analysis and performance and power measurements before you go off and build your product, before you start your RTO, before you go procure IPs, or before you start building your boards. It's really to understand all the unpredictable system responses. What do you need for architecture exploration? First and foremost, you need an environment where you can actually visualize your multi-die architecture. Second one is being able to support multiple levels of abstraction. Why is this important? Because when you're looking at these systems, each one could have different types of requirements, in terms of the level of detail you want to enter, in terms of what are the analysis you want to do, in terms of the available information as well. So depending on how much of this data is available or how much of decisions have to be made, each subsystem, maybe in this case, each die, could be modeled at a different level of abstraction. Of course, one of the key things for system level modeling is you need all the different interconnects or interface modeled completely, plus all the different types of IPs, either it's compute storage or communication or scheduling or other technologies. Now, one of the key things when you're doing architecture exploration is you tend not to have the software. So you want to be able to try out different variations and then figure out, how it's going to behave for all these different variations. Now, of course, one of the things you also want to use is support for all the common interconnect standards like NVLink, UCIe, bunch of wires. And also all the parameters that can be modified should be incorporated available. One of the key things that is required is task graphs. How do you define your task graph such that you can very easily map it to different compute components which may be on the same die or different die? Of course, there's analysis tools and also requirements management, which you need to integrate within the simulation for quick and accurate architecture analysis. Now, when I look at a model, this is a system level model. As you can see, there's a variety of components here. I can drag and drop, say, a processor component, place it here, set some parameters to create a processor block. Similarly, I can go in here, and I can bring in, like, say, a streaming processor, like a CHI protocol. But at the same time, I can also define things like AI engines, compression, processing units, interfaces. So if you notice here, this can be one die, this can be another die, this can be on a third die. But the most important thing, of course, in this case, the AlexNet is what we're looking at, is what is the task graph that's going to be executed on this particular system. Similarly, when I look at the processing subsystem, it's going to have all of its components, its task graph, its own DMAs, things like that. Of course, at the top level, you may also have other types of attributes. For example, in this particular case, I'm doing a DNN. So, what is the attributes associated with the convolutions? So using this and using information that might be related to, say, power, I can get a complete picture of what is it that my system is going to provide. How is the performance going to change if I make changes, say, to using a different DNN, or increase the number of tiles, or use a faster processor, or vary the memory chiplet count. Vary the amount of memory. How do they all behave? This is where architecture exploration comes into play. And that is also the reason why you need all of these components to be able to do an effective architecture study. Let's look at one of the things, which is transitioning from where you are today to a multi-die subsystem. So for example, let's take in this case an infotainment system. So if I look at the entertainment board, it's going to have the camera interconnect. It's going to have an SRAM, which probably is an FPGA, a PCIe. It's going to have memory, display, IOs, a whole variety of discrete or even an integrated components. And each of them have their own speeds, have their own requirements, in terms of data transfers, has its own, sizes, all of those kind of things. So when you look at it, on the board itself, there's a significant amount of latency between all these subcomponents. And so the latency between the components is not a factor when you compare it to what would happen within a die. Of course, the overall is a factor because, you have to guarantee 33 frames per second or 66 frames per second. Just like how it's set up here, you can create each one of these, say this one, this one, this one. Each one of these can be its own die. And putting them all together in a 3D thing could be the multi-chip using UCIe. One of the things you can consider here is, what if I want to add other types of technologies, maybe like a video codec, or for example, like an image pre-processing to, do some sort of a primitive analysis, things like that. So you could just add on another die and modify the programming to now be able to create a new variation of this particular product. So when you look at the block diagram, these are all the components that are being replaced by just this one single multi-die package. In a price-sensitive market, it might be that the single chiplet is an expensive thing. So, breaking down to multi-chiplet is a solution. But also, if you think about it, I took a board, which is like maybe about 1 foot by 1 foot, and I, reduced it down to a single chiplet. So I saved a lot of area, saved a lot of powers, improved performance substantially. So I do now have the ability to add other functionality. Maybe I can add increase the number of displays, for example, or I can have more terrain viewing in the background for like an image, like a target tracking, things like that. So chiplets really offer a huge advantage, but to be able to understand it, you do need to do a lot of analysis. And this is where you got to increase the amount of testing that you do at the system level. For example, here, when I had the board, I can put in the fastest components out there. Now, when I put it together in a single package, I have to worry about cooling, and I have to worry about, what's the maximum clock speed, things like that. So I want to see, for example, what is the maximum amount of data that can be transferred from the video. So when I started off with 21 packets, I got a latency of 41 microseconds, very reasonable. When I increased it to 210 packets on the video interface, the latency went from 41 to 12 milliseconds, a 300x difference. Now, I tried to increase this to 400, and then I saw that the FIFO buffers are maxed out, so the system doesn't operate anymore. It doesn't work anymore. So now, when I try to do some optimization, I find that 250 packets is the maximum that this system can actually handle, or it can provide. So simulation has helped me understand how to size these individual components. Also determine what is the maximum performance I can get, say, with the UCIe as the interconnect between all these individual dies. Let's take a real-life example with a multi-die and try to understand how you can actually do more effective architecture design. So in this case, we've got an autonomous driving system on chip. Here we have the AI engines. So we have to figure out, what's the optimal mesh, how much of memory data do I need from each of the tiles? How fast should the clock be? Should I be using PCIe 6.0 or 5.0 is sufficient? What should be the scheduling algorithm? What should be the speed? How many threads do I need? Looking at this, do I need a DDR4, DDR5? Can I use an LPDDR? How does it change things? The process subsystem, which is really the main piece, because that's the one that's going to be controlling everything inside of this thing. I got to figure out, how much of functionality is required over there. How much of it can I minimize and move it over to one of these other chiplets? And how does the UCIe performance, which receiver to transmitter, transmitter to receiver within the UCIe is 2 nanoseconds. But then going from a die to the transmitter and the UCIe link can be up to about 1.75 nanoseconds. Similarly, on the other side, from the transmitter to the receiver on the slave side can also be the same amount, which is 1.75. Then, of course, there's overhead in the in the backbone of the UCIe subsystem. So there is a lot of additional delays. So when you look at it, you can very easily add the about 32 to 36 extra nanoseconds for data to be going across. So really, it's not too effective for this to be going here and picking up data and coming back, unless it's background data or I'm just doing an IO read and doing a DMA transfer. When you take something like that and bring it into a model, this is what it really looks like. So you have AI engines, which you set up over here. You have the GPU, you have the power process subsystems. Of course, the main one is all the parameters associated with the UCIe itself. And then, of course, you'll have like all the traffic, the use cases, the task graphs, all of those kind of things, the power manager. So you need all of these things to assemble up your full system model. When you think about it, if I had to do everything from scratch, which means, I would have to build up each one of these components, the amount of effort and time is pretty significant. What you really now need to start thinking about is, how do I create a system model very easily? And that's where Visualsim comes into play, where we provide you all of these pre-built building blocks. Because you provided, you're dragging and dropping them and pretty much instantiating these components instantly to create this block diagram. So in a first order design, in a few weeks, you can actually have the architecture ready to go. Now, obviously, when you're trying to do refinements, trying to make changes, moving the task graph to reallocate across different resources, then the system gets a lot more complicated. What are the types of statistics? There's a variety of statistics. Of course, the UCIe stats is very important. For example, I'd be interested in seeing if any data is dropped. I can see, what's the effective throughput I'm getting. Notice here, even though I set it to 32 gigatransfers per second, I'm effectively only close to 1 gigabyte per second. Big difference. This is on a port-to-port basis. The reason being is there's a lot of other overhead. Remember, we talked about the 32 to 36 nanoseconds. So there's other overhead that can also be added in that can cause issues. For example, compared to port 3, port 5 is a lot more efficient, where we have 2.7 gigabytes per second. So there's a lot of difference between these different options that are available to you. Of course, you can look at, what is your processing latency for your application. And this is probably the most important graph, because you really want to understand over time, how effective is this multi-die solution in the context of an application. You can also look at overall power, individual power, how much of MIPS am I getting on each of the cores, what's the latency, and of course, your AI engines, whether you're starting to notice a remarkable increase in the latency, or is it still continues to remain flat. Why is that important? That is important because you have this, the AI engines are expected to do the same task over and over again, which means they're expected to have deterministic latency or deterministic performance. Now, there are a number of things. Of course, the flip size is one of the things you can vary on the UCIe. But at the same time, also, like using different types of adapters has a big impact. For example, here, when I look at the peak here is about 25 microseconds when I'm using it as a combination of streaming and PCIe. But here, you notice that the peak, actually, most of it is right over here, about 13, but I do see some that have gone up to 18 microseconds. So there's a substantial difference between this and this. When you look at it, it's almost a 25–30% drop in performance. So considering which adapter you use is actually significant. So evaluating all these configurations before you go start building it, it's a significant effort that should be performed and is required to be able to do an optimal architecture. Once you created the multi-die architecture, you created the SoC, you need some sort of a platform where you can actually figure out how I'm going to use this in a particular application, be it a gaming, data center, 5G, autonomous driving, like convolution, neural net processing for image recognition, or segmentation. So many different options are there. So how do you utilize this multi-die to take advantage of that? So one of the things you do is a platform that's available to you where you have really two things. One is the processing, which you can target any one of the cores, and then the data read and write. Because remember, if one of the functionality is going on one core and then the other one is going on a different cluster, which is on a different die, you have to worry about how this impacts the transition or the data movement. So in this particular case, as you can see, we're running an image processing algorithm. These are the basic configuration of where the different functions are being mapped. You can see also the data transfers between them, the reads and writes. So when you look at the plotting, you can see what the power consumption is. We're getting about 30 watts of power here. But you notice the average kind of plateaus out at maybe 5 to 6 watts of power. But notice here the latency is constantly increasing. This indicates a lot of buffering or just a long delay involved in your data transfers. So when you're doing these designs and you're doing the mapping, it's very important to have a platform where you can very easily map these algorithms to these different resources. Because if you look at it, you have the cores, you have logic, you have the AI engines, you have some interconnects, you have memory. So you have so many different components. You might even have like an eFPGA in the thing. How does they all work together in enabling your particular application? You really need an environment for you to be able to map this very easily and try different experiments before you start developing it. Because if you develop it on A72 and you realize, oh, wait a minute, I got to put in logic, you'll have to now worry about behavioral synthesis or rewriting the code. Or if you can't really make the change, you'll have to like make do with eliminating certain functionality. So you create a non-suboptimal product. And that's a very important thing to consider, is having a platform where you can do these kind of mapping scenarios before you go off to the implementation. What are the kinds of experiments you can do? Of course, the base is you have some sort of a base configuration. You map it to only the logic and say the ARM core, for example. Then you see, okay, latency is constantly increasing, as you can see right over here. Then what you can say is, okay, I'm going to remap, say, the segmentation function, which is this one over here, the last function, which I'm using the score. I can say, you know what, I'm going to map that onto the AI engine. So you notice there is a change. Latency is not much. It's between 8.2 and 8.6. So you're looking at maybe like a 10% or even a 5% delta. So not very significant. So you're actually doing quite well. Power hasn't changed a lot. The profile has changed though. But one of the things you'll notice, the UCIe, the NOC, all of those have actually increased in throughput utilization. So you want to be able to level that out as well. So what do? You say, okay, now I'm going to use a direct path between the logic and AI. I'm not going to be sending it off to memory each time. So notice here, the latency is flat at 7.2. Just a couple of spikes here and there, but otherwise totally flat. Problem, average has gone up. Now you're looking at about 8 or 9 watts of power is the average. The peak still is approximately at that 30. But what you're going to notice is the latency is deterministic. So you've really met your particular requirement. And also the utilization on the UCIe, on the NOC, all of those are completely acceptable. Let's take something that is a much larger system, because understanding this will help you understand how, when you're transitioning over to multi-die, you can do a more effective experimentation. So when you take something like an avionics system, not only do you need to design the architecture to be able to meet all the latency, temperature, power, utilization type requirements, but you also need to have assurances. How does your microelectronics assurance go for either all the different components, different subsystems, or the whole avionics system itself? So when you look at a multi-die architecture, you have to worry about not just that, yeah, I get better performance or I get better power situation, but also how does this impact my microassurance? And this is where you want to look at, systems like these tend to have redundancy, they're dual and triple redundancy. So putting them into the same package, or having, two discrete components, which are both multi-die, and then evaluating, what happens for different types of faults. So you can look at the failure analysis, look at reliability, which effectively tells you what your microassurances are. The other aspect, which is very critical in more of these kind of situations, which are more unpredictable kind of environmental conditions is to also look at the power system. So, you create faults where some of the power lines, the supply lines are cut off. How does the system continue to operate? Does it still work within the confines of the requirements that we've had? So if you look at these types of analysis, what you'll notice is the latencies, the power, the temperature, which task completed at what period of time, what was the utilization, how much of buffering was done. So you get a variety of standard stats. Again, going back to what I was telling you about what is required for architecture exploration, these are all the elements that are also required for architecture exploration. Not only do you need all the modeling components, but you also need the standard statistics. And also at the same time, you need the platform where this can all work together. How does this connect to the rest of the system to create the final product? The multi-die is a chip that is sold, but eventually has to be integrated into a system or into a subsystem, and then the subsystem will have to do some definitive operation, avionics, braking system, autonomous driving, things like that. When you take any system, there's a variety of experiments that you can do. Now, obviously, the power utilization, throughput, the buffer occupancy, latency, all of these are important. But a lot of different things impact the number of cores, like increasing the bandwidth on the interconnects, things like that, or, generating, having faults that actually take out one of the cores, things like that. You can look at what's the latency for each of these scenarios. You can look at, what's the utilization of the bus or the processor, and then use that to make a decision as to how to size each of these subcomponents, which eventually they're going to go on individual dies, be able to size those dies as well. So even before you transition from, say, a board or a multi-board solution to a single chip, is it possible that you can reduce some of the requirements on the system, so that way you're not creating a very, very complex chip or a chip that requires 7 nanometer when you could have done most of it in 28 nanometer. One of the areas which is very critical and important is the deep neural net. So today, AI is paramount. And when you look at AI, there's a lot of different ways you can implement the AI code. You can put it on a processor, you can put it on a GPU, you can put it on tensor, you can put it on, other custom DNN AI engines that are coming on the market, a lot of startups, things like that, right? Now, when you look at, say, a CNN, a convolution neural net, you have different types of them. You have ResNet, you have AlexNet, GoogleNet, Mask, RCNN, things like that, which pretty much has the same types of things. You have some sort of input, you have some pre-processing, you have a series of convolutions, and then you have post-processing, and it goes out. But how you define the flow, your task graph, how you describe all the layers, the functionality, all the criteria associated with each one is very critical, because this determines, do I send it over to the GPU? Do I send it over to the processor? Do I send it over to the, the TensorFlow, which has specific functionality for multiply, accumulate, things like that. Then what you do is you take this flow and you map it to different dies that are within your particular package or your planned package, your proposed package. And then you run simulations to look at, what happens to the performance, what happens to the power. So you can see my off-grid memory access was about 1 millisecond while the power was at 10. And notice it took about, 2.4 seconds to complete this particular RCNN processing. Gave me about 0.4 frames per second. Not a very efficient type of architecture that I would say. Power was high, amount of frames per second was pretty low. So now what I do is I take something where earlier on I had 168 cores, but only 30% of it is available in memory, to where I took a 64 core and made 90% available in memory. Power drops, so we went from 10 to 4, latency 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 took longer because number of cores have reduced. So I've got it down to 3.4 seconds, which means I went from 0.4 frames per second to 0.3 frames per second. Power reduced, but the effective number of frames per second and the processing of the frame took significantly longer. What if I make it where I don't need external DRAM? I just need to load it and then load it over to the SRAM. All processing is happening within the SRAM, and I move it from the 8 by 864 to back to the 168. You can notice now latency has dropped to 0.1 seconds, and I can get almost 10 frames per second processed. This is what we're looking for. Of course, the power has gone back up to 10 watts. But if you think about it, what is really happening now is that I'm able to achieve extremely high performance, and my goal was to try to increase the amount of SRAM in my particular design. So this is where a multi-die becomes valuable, because now all of that SRAM can be a separate die, which I can procure much easily, or I can design it, as opposed to making my existing CPU or GPU die or the TPU die huge, because I got to fill it up with so much of SRAM. I also tried some experiments where I looked at reducing the amount of SRAM completely, but unfortunately the performance dropped to where it dropped down to 22 seconds of processing time, and it was 0.04 frames per second. So not even part of the proposed solution as well. A little bit of an introduction to Mirabilis Design. Mirabilis Design is a Silicon Valley and Chennai, India-based company. Our goal is to enable electronic design using architecture exploration and simulation. We've got significant background in both semiconductors, automotive, and aerospace. As you can see on the right-hand side, our environments, the single environment, single set of IPs support the semiconductor level, all the way to the mission or the embedded system level. A number of things can be done within this environment. Of course, optimizing the specification is the first one, but now you can collaborate across, like somebody has a satellite to, like, say, payload to a semiconductor, high performance computing semiconductor, or a car to, like, say, a braking system or autonomous driving to a component that does all the image manipulation or image processing. So optimization, collaboration, and then looking at all the use cases. Do I need another die? So, I've got, like 64 AI tiles. Do I need to put another 64 seconds? Do I need to add another die? As you can see, now it becomes very easy for you to say, okay, how many dies do I need? What should be on each die, and things like that. Now, a quick introduction to technology and methodology. As I mentioned, architecture exploration is what Mirabilis does. So but you can do it at any level of abstraction. You can look at an IP, or you can look at a complete vehicle movement with, V2V processing and all of those kind of things. And the purpose is 3 things: power, performance, and functionality. So each one has their own requirements. Each one has their own understanding of what is required. And really the purpose is to make new decisions. If I move to a multi-die, are all of my use cases going to work? Only some of them. Work meaning, are they going to meet the requirements? What is the feasibility of this particular design? Can this even be built? Remember, we talked about task partitioning. How do I take this entire application and then split it up across multiple clusters, which may be on the same die or independent die? And of course, the question always comes up is, how do I go from here down to implementation, which is, how do I make the transition of flow? VisualSim itself is a very tightly integrated product, has a lot of very good APIs to connect to the rest of the world, has a large library of components. So this is where the value add of Mirabilis comes in, which is a huge number of components available, allows you to pick and choose whichever components you need at that point, so you have all the building blocks required for you to put your whole chip together. This here is just a listing of all the IPs that we have in VisualSim, which you can see has complete coverage from like very abstract to microarchitecture, but also IP and SoC all the way down to a full system. One of the areas that is very critical and something that is has a lot of advantages doing it at the system level is power. When you look at power, there is generation, storage, consumption, and management. Now, when typically people are doing power analysis, they put an Excel spreadsheet and try to calculate the power. That worked fine when you were running a car, which was an IC engine. It was just, producing power on demand. But now almost everything you're using is a battery based. So you really have to look at, how do I maximize my battery capacity and my battery life cycle so that I can maximize, say, my distance of travel or amount of time that my cell phone is turned on, or the max amount of time I can be watching a video on my iPad or things like that. To enable that, you need power management. So power management can be based on utilization, can be based on inactivity, can be based on state machines, so any of those. And that leads to understanding the thermal aspect, which is, temperature and heat effects, both localized within an IP block, but also within the whole semiconductor or within the full system. Now, debugging the power spikes, things like that, definitely is very valuable. So you can reduce the amount of capacitance by potentially just using a scheduling algorithm to shift some of the software applications. You can also generate in Visual Sim a whole bunch of technology that can be utilized downstream for verification. For example, the UPF file, the system verilog test benches, the power states for VCD dump for debugging purposes. So a variety of data can be output from the power solution as well. Now, why would you use Visual Sim to do multi-die analysis? One of the key things we hear from our customers is people are doing modeling, but the problem is they don't have any of the IP libraries to be able to effectively do it. So as a result of which, it takes too much time. And with Visual Sim, since all the IP is already available, you can connect them all up very quickly. You can get to your implementation much earlier, but at the same time, all of your communication refinement is done before your implementation starts. So based on over 250 products that have been built with Visual Sim, people have shown between 20 and 40% saving in project schedule, which means that you have much greater control over how you're building your product. So Mirrorless Design partners with customers to really help you create the next generation multi-die. We have experience in architecture exploration, very good technical support. We have worked with over 65 companies across the world, and we're used in over 250 products. One of the key things that we do is a continuous innovation. Could be simulation speed, adding new IPs, enabling requirements to go with an AI engine to run with the simulator. And the other aspect is how do you put everything together, which is the hardware, your network, your embedded systems, and your software within the same environment. With this, I would like to wrap up my webinar and would like to thank all of you for attending the session. And feel free to stop by and ask any questions. And at the end of this webinar, we will be sending you a link